So here's a problem. There are 4 points A, B, C, D on a circle, dividing it into 4 arcs. And if we take the midpoints of those arcs, P, Q, R, S, and connect each to their opposite midpoint, do the 2 resulting chords always make a right angle? Today, let's talk about how this problem led me to a theorem I've never heard of before. My name is Dirdos. I'm on a mission to collect interesting math problems for school-aged children, and I'd like to take you along. Since PQRS are midpoints, the arcs AP and PB must be the same length. Let's call this length W. Similarly, arcs BQ and QC can be X's. CR and RD can be Y's. DS and SA, Z's. If we look at only the midpoints, PQRS, they divide the circle into 4 regions, where the opposite 2 regions always combine to give us one of each of the W's, X's, Y's, and Z's. Between P and Q, there's a W and an X, so the opposite region, between R and S, has a Y and a Z. Between Q and R, there's X and Y, so the opposite, between S and P, there's Z and W. Why would having half of the circle between the 2 regions guarantee that the lines intersect at right angles? This is where I was stuck, because I couldn't figure out if this was supposed to be a special case with half circles or right angles, or if there is something more widely applicable at play. So I did what any curious, sane person would do in this situation and snuck a peek at the solution section for the problem on the Art of Problem Solving website. And when that turned out to be empty, as it sometimes happens with older problems, I looked for the problem post in the forum. There I found this solution by Santos C. Gwyn from about 17 years ago. And it mentioned everything I found so far and went straight into something like, therefore, divide by 2 and the intersection is 90 degrees, QED, in the next line. I was so confused. It's like I'm trying to build a bridge where I'm clearly missing some stone pieces, so I look at someone else's bridge, and it just points to the 2 stone pieces on either side of the gap and says, they're the same stone. Step on this, and it teleports you to the other side. What's more, the comments after that all seem to have understood them perfectly. It must be the case that I'm missing something here. A theorem, maybe. If I were to guess what this theorem says, it's probably something like this. Given 2 disjointed arcs A and B in the same circle, with central angles small a and small b respectively, if we connect the 2 edges of arc A to the 2 edges of arc B, such that the 2 lines intersect, then each of the angles of the intersection subtended by arc A and arc B has a measure of half of the sum of the central angles, small a and small b. That looks just like the last piece of stone we need to finish building our solution bridge. But to make sure it is a solid piece of stone, we need to ask a couple of questions. Does it sound right? And why is it true? In that order. First, does it sound right? This is where I try to convince myself if it's true, using examples. If this theorem is true for the 2 arcs we chose, it should also work for the 2 arcs we left out in the circle. The 4 central angles add up to 360 degrees, and the 4 angles of intersection should also add up to 360 degrees. Does this work? Since we're only taking the average for each pair of central angles, we're not changing the sum. So yes, they still add up to 360. If this theorem is true, then it doesn't matter where the 2 arcs are in the circle, as long as their sizes don't change. Their angles of intersection shouldn't change either. That means if I hold one of the 2 arcs in place and move the other, the angles of intersection should all be the same. Combine that with the fact that they're all subtended by the same arc, the intersection points should form part of a circle. I should also be able to make it so that one of the 2 arcs is almost half of the circle, and the other one is tiny. And I should get something that looks more and more similar to an inscribed angle on the diameter, which should be a right angle. Or I can take two arcs that add up to half a circle and move them closer and closer to each other until they're touching, and the result should also match the inscribed angle on the diameter. All of these tests worked out, and I'm relatively convinced that this piece of mathematics is solid. We still can't use it in a solution yet though, because we need to know that somebody somewhere has answered the question of why it's always true, or in math terms, given a proof for it. We can always try to do it ourselves because if somebody somewhere, then why not me and why not now? And if we get stuck again, we can ask the internet for help. Again. Remember we said earlier that the central angles in a circle add up to 360 degrees. Let's just give them some names corresponding to the arcs. Now, if we draw the chords on arc A, this angle here is an inscribed angle on arc C, which should be half of the central angle C. Similarly, this is half of central angle D. Let's call the angle we want theta. Now we have two equations, one for the central angles and one for the inside of this triangle. A bit of algebraic fiddling around and we find that yes, theta is in fact always half of the sum of A and B. Now just to check that this really is a widely known theorem out there that people just assume they can use in solutions. Let's try to guess the name of it and search it up online. Opposite arcs theorem is probably too vague. Intersecting chords theorem is already used for something else about the lengths of these chords instead of the angles. So I tried angles of intersecting chords theorem. And guess what? It's a thing. And it's exactly what we were talking about. Phew, math makes sense again. Now I wonder if there's an analogous thing in 3 dimensions. Let me know what you think in the comments below. And until next time, stay curious.